All right, well, I hope everybody's doing okay today. A few items. What is happening on Monday? Okay, it's the first exam. Now remember, this is a short 6 weeks. After this week, we've only got 3 weeks left. We've already got 6 weeks helping to determine what your semester grade is going to be. So this exam is going to have 9 questions. It's going to be a little more difficult, okay? I'm going to let you use your notes on this test. But because I'm letting you use your notes, that means you should probably study harder because it's going to be more difficult. You don't want to get trapped in 45 minutes looking through your notes and not answering the questions, okay? Now, on the newest upload for Google Class website, the week of Monday the 14th through Friday the 18th, you'll notice right here, number 2, I give you a complete listing of everything you need to be able to do on that test. All right, so those are the topics you really want to go ahead and focus on. In fact, you'll notice the last one is linear and angular velocity, which we're going to go ahead and spend as much time as we can on today. Now, tomorrow you're getting your last focus activity. We're turning those in on Friday. Again, we're going to spend the entire period just looking at these types of problems. But if you haven't already done so, if you go to this current week, the 7th through the 11th, okay, click on the lesson that we're currently discussing, arc length and circular motion. Okay, what am I referring to? What's at the end of each of these files? Okay, the homework assignment. Okay, we finally reached the point where I'm not going to be providing a copy of those anymore, so you have to go to the website, write down the problems, or you're going to print your own copy, whatever it is you want to do. But I really want to encourage you, don't just ignore this. Okay, this is due tomorrow. Now, it's going to be due at the end of class tomorrow, because what I'd like to do is spend some time looking at some of these word problems together. I want to make sure you feel comfortable with these. Okay. Number 12, I would say, is the most difficult on the assignment. So if you're looking for a little more of a challenge, that one's a good one to look at. Okay. So any questions on that? Okay, please remember when it comes to retakes, and I'm already anticipating several people are going to want to retake the exam from Monday, you have to have the assignments done in order to do that. One of them is this one right here. Okay, you have to have that turned in before or by the time you retake. The reason I bring this up is because it's already happened yesterday. Somebody came in to retake the compositions quiz. I went ahead and graded it. I go to put it in the grade book. They don't have the assignment turned in. I'm not going to find this individual. Basically, that retake is gone. Okay, you have to have it turned in by that time. You cannot turn it in after you retake. All right. So please keep that in mind. I don't want you to be in that situation. Okay. As far as the rest of this week, like I said, the focus activities, Mr. Yacht will be here tomorrow. If you're not going to be here on Friday, that is a crucial day. That's when I'm going to introduce the unit circle. So please be looking at that website, look at the video, come on in if you have any questions. That is pretty much going to determine what we do from here on in trigonometry. Okay, so there's a lot of stuff coming up. Okay, but we still have time to get it taken care of. So let's start talking about some linear and angular velocity. Okay, so let's talk about the formulas first, kind of just like a little recap of what we did yesterday. Linear velocity is speed. Okay, we related it to the distance equals rate times time yesterday. But for our purposes, we're talking about speed following a circular path. All right, because a lot of what we're doing are going to be wheels or, records or DVDs, some kind of circle that's going to be rotating at a particular speed. So V represents linear speed, linear velocity. Okay, so we had a couple of different formulas yesterday. The first one I introduced was the distance, the arc length, divided by the time. Okay, now we used that for a short time, and then we went ahead and changed it based on angular velocity. So let's take a moment to talk about angular velocity. What variable do we use for that? Omega, okay. The lowercase Greek letter omega, that's curvy W right here. Now, to find the angular velocity omega, the formula is the change in theta divided by the change in time. Okay, so what is angular velocity? It's the measure of your central angle, how fast it's rotating with respect to time. That's angular velocity. Remember, linear velocity is a speed. But we actually use this to go ahead and help me figure out a new formula for linear velocity. Okay. All I need to do to find linear velocity is take the angular velocity and multiply it by what? What was the one item we showed yesterday? The radius. As soon as you multiply it by the radius, you've introduced a unit of length. Now you have linear velocity. Okay, so that's why angular is going to become so important to you. Well, how do we find angular? I know the formula says theta over time. Well, there were two fractions I was going to have you set up each and every time we did this. First, you need the number of revolutions. Okay, how fast is your item spinning in how much given time? Okay, and that's exactly what the formula is saying. Okay, theta, the number of revolutions, over t time. But now, what's that one ratio that I always multiply by no matter what? 2 pi radians over 1 revolution. This is how we're going to start to find angular velocity every single time. Okay, remember, this comes straight from the formula, so you don't have to worry about the formula itself. Okay, the first thing that's going to cancel are your revolutions. So it's always going to be in radians per time. So this is your angular. If I multiply that by the radius, then I'm going to have linear velocity. Okay, any questions so far? All right, how far did we get? We were almost done with B? Okay, did we have the problem written out? Okay, so let me just go ahead and kind of catch up to where we were yesterday. So B does use the same angular speed, angular velocity as the previous one. So I believe we said we had 33.33 revolutions, okay, in 1 minute. Okay, so there's the number of revolutions over the given time. We're going to multiply that by 2 pi radians over 1 revolution. So this is radians per minute, which is exactly what A wanted. So if I stop there, that is the angular velocity of our problem. We're talking about a vinyl record and how fast it's spinning. But now B says, okay, I want to find the linear speed. That's the same as linear velocity. Okay, so I'm going to start with the angular velocity we found in A. What do I need to multiply this by to make it linear? Okay, so what's the radius? Okay, the radius is 15 centimeters. And what I like to do is go ahead and create a fraction for that radius because you're going to have a bunch of other fractions you're dealing with anyway. Okay. Now, if I were to go ahead and stop right here, a couple things. The revolutions have already canceled. Once you introduce a unit of measure from the radius, okay, the radians now have units. Okay, because up until now, the radians don't have units. But now I know the radians are going to be measured in centimeters. Okay, so we can kind of disregard him. Now, this is going to be in centimeters per minute. Is that what the problem wanted? No, it wanted centimeters per what? Per second. So you always want to be careful. Okay, what's the problem want? So I got to add one more ratio on here. If I want my minutes to cancel, well, I'm going to put those above, seconds below. What is that ratio? Yeah, 1 minute is 60 seconds. Okay, remember, this is what we call dimensional analysis, where we're using these ratios to change the units we have. So let's see, those minutes are going to cancel. So it looks like I'll end up centimeters per second. All right, so once we have it written out, well, now it's just a matter of calculating it. So I'm going to multiply 33.33. Okay, let me go ahead and put this all in one big fraction. So 33.33. Then it was times 2 pi. Remember, pi was at the bottom left of our calculator. Times the radius of 15. And I believe that was it, right? Divided by 60. Okay. So what should I get when I push enter? Okay. So let's say this is rotating at a speed of 52.4 what? There we go. So about 52.4 centimeters per second. There you go. Okay, and the nice thing about these problems is the consistency. Okay, remember, you can always solve them in the same fashion. I hate to call them like cookie cutter problems, but I mean, you just apply the information in the same way. Okay, so let's try another one together. All right, so this one we're talking about a bike messenger. Okay. And what do we got here? Bike messenger rides the bicycle shown. Looks like we have a wheel with a diameter of 30 inches. So my radius again is 15, but in this time it's inches. A, during one delivery, the tires rotate at a rate of 140 revolutions per minute. Find the angular speed of the tire in radians per minute. Okay, so angular speed. So I'm already thinking what for the first fraction? How fast is it spinning? Okay, so 140 revolutions. In how fast a time? In 1 minute. Okay, so 140 revolutions in 1 minute. Remember, we always start out the same way. What am I going to multiply this by now? Okay, we're going to go ahead and introduce the radians. 2 pi radians over 1 revolution. Okay. Now, the first thing that should always cancel is what? The revolutions. So the revolutions are gone. I've got radians per minute. Is that what they wanted? Yeah. Okay. So I don't have to do anything else for part A. All I got to do is multiply. So 140 times 2 pi. So we're looking at 280 pi. Okay, 280 pi. What should I be getting? Okay, 879.6 radians per minute. Okay, all right. Let me go ahead and put this right here. 879.6 radians per minute. Okay. Is anybody having trouble with angular velocity? Okay. How fast the measure of the central angle is rotating with respect to time. Okay. So part B, on part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. Okay, so what happened? Can I use what I found in part A? No, because it's rotating at a different speed. So now I kind of have to start all over. In order to find the linear speed here, it doesn't say anything about angular. I would go ahead and encourage you to find it because you're going to need it anyway. Okay, let's find the angular speed of this new trip. So what's my first fraction? Okay, so we have 2.5 revolutions in how fast a time? Per second, so 1 second. Okay, times. All right. What's that consistent fraction we always use for the second one? 2 pi radians. Okay. 2 pi radians in 1 revolution. Okay. Now, if I were to stop right here, this is the angular speed, the angular velocity of this problem in part B. Okay, if it's rotating at 2.5 revolutions per second. Okay. That's my angular velocity. Remember, this is theta divided by time. All right. Well, how do I make it linear? Multiply by the radius. As soon as I do that, I've introduced a unit of measure. Here it's inches. So 15 inches over 1. So let's see. The revolutions are going to cancel. Because I now have inches, the radians have units. Okay, so I don't need to label them as radians anymore. Now my answer is in inches per second. What's it want? Miles per hour. So we're going to have to convert both of those. Okay, so again, in the beginning, I'm going to take it 1 fraction at a time. If you feel comfortable already or eventually to combine several fractions so that you don't have to do this, please feel free to do so. I just don't want to lose anybody. What do you want to start with, time or measurement? Okay, so let's start with the inches. I got to go from inches to miles. So I'm going to do that through feet. Where should I put the inches on the next fraction? Bottom, because I want those to cancel. All right. So we know that in 1 foot, there are 12 inches. Okay. Now I want to go from feet to miles. So I'm going to go ahead and put feet down below, miles above. In 1 mile, there's how many feet? 5,280. There we go. So that takes care of the inches to miles. Now I got to convert seconds to hours. Okay. So again, I could go ahead and do this in 1 step. I could go ahead and say 3,600 seconds in 1 hour. Okay. Again, if you want to do that, please feel free. I'm going to go ahead and write it out. So I'm going to go through 1 second. Okay. Or excuse me, what am I talking about? 60 seconds in 1 minute. Okay. And then I'm going to have 60 minutes in 1 hour. Right. So let's go ahead and see if I'm going to end up with what I want. Now, even though they're pretty far from each other down the line, the seconds are still going to cancel. Go ahead and raise this a little bit. Let's see. The inches are now out. Feet are gone. Oh, minutes are gone. And it looks like everything's canceled out. So I'm left with miles per hour. Remember, this is what we call dimensional analysis. Okay, changing the units to what we want. Okay, so now it's just a matter of calculating it. So let's see here. Come on over to my calculator. Okay, so we had 2.5 revolutions times the 2 pi. I'm just going straight across. Times the radius of 15. And then I believe it was times 60 times 60, right? So I'm just going to go ahead and say 3,600. And then down below, I did have to multiply the 5280 times what? 12. So 5280 times 12. Okay. So what am I getting when I push enter? How fast in miles per hour is he traveling? 1.34? Oh, we're a little off. 13.4. 13.4 is what I got. Okay. Connor, did we just type something in wrong? Okay. So about 13.4 miles per hour. There we go. Any questions? Is anybody having a hard time? Anybody not seeing where I'm getting these values from? Okay. Are we ready for one on our own? Okay. Let's try this one. Okay. Consider the DVD shown. Find the angular speed of the DVD in radians per second if the disc rotates at a rate of 3.5 revolutions per second. And then part B, if the DVD player overheats and the disc begins to rotate at a slower rate of 3 revolutions per second, find the disc's linear speed in meters per second, or in meters per minute, excuse me. Now this one's actually like number 2. You can't use the same angular velocity you find in part A for part B because you're rotating at different speeds. Okay, now you're also going to notice one thing. You're going to have to convert meters and millimeters. Okay, does anybody need that ratio or, okay, 100 to 1, not 100 to 1. If you're going to go straight from millimeters to meters, 1 meter is 1,000 millimeters, or you could go through centimeters. Okay, 1 centimeter is how many millimeters? 10. And then how many centimeters are there in a meter? 100. Okay, so there's different conversions there depending on how you want to do that. Okay, so let me go ahead and give you 4 minutes. This is definitely a good time to go ahead and talk with your villain buddy, especially if you're having trouble. Okay, see if they're setting up the problem the same way. Are we getting the same answer? If we're not, okay, let's talk about why that is. Okay. Now, I don't know if we're going to be able to get to every one of these problems, even, using class time tomorrow to do this. I'm thinking tomorrow we're probably going to be spending time looking more at the assignment than anything else. Remember I said number 12 on the assignment was a really challenging problem, okay, or at least it is what I consider to be the most difficult. I set up a system. If you have this copied, okay, and I'll put this back up in just a second, if you're looking for a little more of a challenge, okay, now 4A, this one's talking about a clock, not really that challenging, it's the same idea, but part B. If the linear speed of a second hand is 20 inches per minute, is the clock running fast or slow? How much time would it gain or lose per day? Okay, so that one's definitely a little more rigorous if you're feeling this is too easy for you. Okay. And probably, not tomorrow, probably Friday, I'll go ahead and post the answers to these, so whatever ones we don't get to, you'll be able to look at over the weekend in preparation for what? The test. I only put one of these on the test. It's number 9. Okay. And remember, where can you find a complete listing of what you need to look at for the test? That's right there on the website. Okay. Do, 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 do. Do, do, do. Everybody's turned in your Chromebooks, right? Looks like those are. Oh, it's okay. Okay. I'll tell you what I did on A. I rounded mine to the nearest whole number. Okay, and then on B, I rounded it to the nearest tenth. Excuse me. All right, so even if you're not done, that's okay. Okay, hopefully you're at least done with A. All right, so we're wanting to find the angular speed of this DVD here. So how many revolutions do we have? Okay, so 3.5 revolutions. Always start the same way. In how fast a time? 1 second. Remember, that's exactly what we're showing in the formula, the change in theta divided by the change in time. Okay, so 3.5 revolutions per second times what? 2 pi radians. Okay, in 1 revolution. Okay. Now, first thing, revolutions always cancel. It's in radians per second, and is that what the problem wanted? Okay, absolutely. So now we just go ahead and multiply. So 3.5 times 2 pi, I'm looking at 7 pi, which I believe comes out to 22. Yeah, 21 point. It was like a really high decimal, right? That's why I went ahead and rounded it to 22, but radians per second. There we go. Okay. How many people got that one right? Fantastic. Okay. Who wants to come on up and show me B? So we have to start with a new angular speed and then work into the linear. Okay, Connor, you want to do it? Okay. All right, come on up. Okay, so now we're only spinning 3 revolutions per second. Okay, times my 2 pi radians over 1 revolution. Okay. Okay, times 60 millimeters. Okay. Okay. So as soon as he multiplied by that radius, it's now linear velocity. Okay, so it's in millimeters per second, and we need meters per minute. So 60 seconds in 1 minute. That'll take care of the time. Okay, and he went ahead and did it directly. There are 1,000 millimeters in 1 meter. Okay. Right. Revs are out. Seconds are gone. We have millimeters, so radians are gone. Millimeters are out. Meters per minute. Okay. So 3 times 2 pi times 60 divided by 1,000. Looks like he's getting 67.9 meters per minute. What do you guys think? How many people got that right? Fantastic. Anybody having trouble? Anybody confused? Okay. All right. Fantastic. That's amazing. All right. Let's get into number 4. Okay, so it says a wall clock has a face diameter of 8.5 inches. The length of the hour hand is 2.4 inches, the minute hand is 3.2 inches, and the second hand is 3.4 inches long. A. Have a pass. Okay. Okay, let's see, where were we? So A, determine the angular speed in radians per hour and the linear speed in inches per hour for each hand. Okay, so we got 3 hands, so I'm going to have to do both operations for each of them. So A is a pretty large problem by itself, and then I said B was a really good challenge problem if anybody was interested. Okay, if you do calculate that and you want to come show it to me, I can let you know if you're right or wrong. And at some point, I'll go ahead, like I said, post the answers so you can see how I got it. Okay, so let's go ahead and say we start with the hour hand. It's the first one listed. Okay, so the hour hand. First thing I want is the angular velocity, because I'm going to use that to find the linear velocity. Okay, so let me give you 30 seconds. Write out what you think my ratio, that first one's going to be. Don't say it out loud. Because typically these problems will give you the number of revolutions in how much time, but, okay, we know how a clock works. Let's see what you can come up with as far as your first ratio. Okay, how many revolutions, how much time? Okay. Everybody at least think they have the first ratio ready to go? Okay. Here's what I put, because we're talking about the hour hand, right? So he's only going to make one full revolution in 12 hours. Okay, remember all these hands are moving at different speeds. They represent different measurements of time. So a revolution is going to be different for each of those. Now, I went immediately to hours, okay, because the one thing I was looking at, it did say radians per hour. But I mean, you could have done that in minutes. One revolution in, what would you have done to go immediately to minutes? 60 times the 12. 12 hours times 60 minutes each. Okay, so there are all kinds of different ways you could have started, but thought hours was the easiest. How many people got that? Okay, good, good, good. Well, now what would I do? Okay, multiply by that consistent fraction, 2 pi radians in one revolution. Okay, so the revolutions are gone. Okay, this is in radians per hour. Okay. So this one, we can just go ahead and simplify. 2 pi over 12. So I'm going to go ahead and say pi over 6 radians per hour. Okay. And now we can just go ahead and approximate that. So let's see here. Pi divided by 6. Okay. So about 0.52. 0.52 radians per hour. Okay. Would everybody agree? Now I want to find the linear speed of this guy. Okay. And I want him in inches per hour. Okay. So I'm going to go ahead and start off the same way. I need my angular velocity. Okay, 1 revolution in 12 hours times that 2 pi radians in 1 revolution. Okay. And there's my angular. How do I make it linear? Got to multiply by the radius. Well, what was the length of the hour hand? Okay, 2.4. So all of these have different lengths, so it's not the radius of the clock itself, but what we're talking about is imagine that each of these hands, the tip, forms its own circle as it rotates. That's why we're going to go ahead and use the length of that hand as the radius. Is everybody okay with that? So I'm going to multiply it by 2.4 inches. Okay. And do I have to do anything else? It wanted the linear speed in what? Inches per hour. And that's exactly what I have. After the revolutions cancel, okay, now that I have inches, the radians now have a unit. Okay, and it's just a matter of, multiplying through. Okay. So I can just multiply the pi over 6 that I previously had by 2.4, right? Okay. So I have the decimal value right there times 2.4. Okay. So I'm getting 1.26. But 1.26 what? Inches per hour. There we go. And then you would do something similar for the minute hand and the second hand. Okay. All right. How are we doing? Is anybody confused? Any questions? Okay. Remember, what are we working on tomorrow? Okay, we're working on the assignment. Okay, so please, probably in your best interest, if you go ahead and bring it tomorrow, as soon as we finish, you just turn it in. Now, we're not going to have time to do the entire thing, but we're going to spend the bulk of the period talking about that. Okay? Yes, ma'am. Uh-huh. Yeah, remember on this first part right here, this is angular and this one's linear. Okay? Because remember, these first two fractions give you angular, but as soon as I multiply it by the radius, then it becomes linear. Because now I've got length per time. So a distance. Does that make sense? Okay.